Okay, welcome to the H&J Global Chair lecture series. I'm Chamu Yu from the National Yangming Jiao Tong University, and the speaker is Professor Florian Tramèr from the ETH. And in the previous two lectures, Professor Tramèr already gave us some course material about the large language model safety and alignment issues. And today's lecture, I believe that the Professor Tramèr will let us know more about the privacy issue of the large language model. Let's welcome his lecture. And Professor Tramèr, time's yours.
Yeah, thanks a lot, and thanks for coming to this third lecture in the series. So yeah, as mentioned today, I'm going to be focusing more on privacy aspects of large language models, of sort of data privacy aspects. In a first part, we're going to be talking about how we might even think about defining what it means for a machine learning model or a large language model in particular to be private or to be privacy preserving. And then in the second part, we'll talk about some particular privacy issues like memorization in large language models and possible defenses. We'll talk about differential privacy and conclude from there. So why should we talk about privacy, about data privacy in machine learning? It's primarily because machine learning models and large language models in particular are data hungry. Like the amount of data that gets um, injected to train these models at any stage of training is huge, and there really seems to be a path towards just always using more and more and more data. And from what we hear from some of the leading model developers, um, they're essentially running out of data to train on. So they really just try to collect and use all kinds of data that they can. And this, of course, conflicts with privacy. If you're one easy way to collect more and more data would be to train on more and more data would just be to collect this data from your users. And some companies have actually done this in the past and probably still today. So a prominent example is Google's Gboard learning models, so the models that are used for keyword for keyboard prediction, and these famously use data collected by users in a process known as federated learning that we'll talk about a bit more later on. Um, and in their case, it kind of so far has worked reasonably well. They haven't had any data breaches, as far as I know. But this can be a lot worse. There was an example of a South Korean company that released a chatbot a couple of years ago, where the chatbot would sometimes just leak conversations from from users because presumably they had done something a bit wrong with how they trained this model. So these are the type of privacy risks that exist for training data. These are some of the most prominent ones and ones that people also worry about a lot. There's of course also privacy risks at other stages of the model pipeline. Um, we um, we heard a lot when ChatGPT came out of different companies being wary of sending their data to ChatGPT because, well, then OpenAI or Microsoft just essentially can see this data in the clear. Um, and so at inference time as well, you might want a certain type of privacy that you can essentially send your data to to a machine learning model or interact with a machine learning model without having to release your data, your inference data in the clear. And then yet another privacy concern that we already talked about in the previous lecture is the privacy of the model itself, which you might be able to steal. So these are kind of different things people might mean when talking about privacy in the context of machine learning models, of large language models. in this lecture, we'll primarily be concerned with the first notion of privacy we talked about, namely privacy of the training data. So here it's worth asking, since large language models today are primarily trained on public data or on publicly available data from the internet, is this even a concern? Like, are there privacy risks associated with just training on public data? And I would say that yes, there are, and that there's many things you can do with data that's publicly available that can still infringe on people's privacy in a very broad sense. For example, you might suddenly enable people to aggregate different sources of public information in more efficient ways, to let them sort of infer things about the individuals that were previously not possible. You're essentially making some forms of publicly available information more available or more easily accessible. And in some sense, this connects to this broader notion of privacy that's known as contextual integrity, which essentially says that every piece of data that people produce usually has some intended context of use. Like if I post some text online or some pictures on social media or so on, I typically do this with the intent of, say, just sharing this within a certain context, within a certain group of people. And if someone then just comes along and puts this data into a machine learning model and later on leaks it to the world in a different context, this can be a violation of my privacy in a broad sense. So just to give an example of why even just processing publicly available information can have very, very strong implications for privacy. I have one example that I really like that has to deal a bit more with image vision models, which is reverse image search. And this is something that I would find that I think is probably doable with today's technology, and is incredibly scary. And in some sense, the fact that it doesn't exist yet is just because people have been probably a bit wary of doing this. So the idea here is, right, whenever people post images online, be it on social media and so on, these will get associated with a person's name and maybe other information about this person, like where they live, where they work, and so on. But this is usually in a specific context, and just somewhere on the web. And so if today someone just, a stalker or someone takes a picture of some person in the real world, it's not trivial, or it's not super easy for them to just go and find who this person is online. There's no sort of photo phone book in some sense of who someone is, just given a picture from them. But this is something that using sort of modern machine learning models, modern vision models, would be very, very easy to achieve. And there are some somewhat shady companies that actually already today promise to do something a bit like this, that you can just input any picture you've taken of anyone and it'll just find all publicly available information about that person. And so this is an example of how just being able to aggregate and make accessible public pieces of information can be quite scary and cause sort of very clear privacy issues. And I think we'll start seeing similar things happening with large language models as well. And so here really the fact that we train on publicly available information and might sort of leak publicly available information can also be an issue. Okay, so for now, we still haven't really fully defined what it means then to train a machine learning model or a language model to be private. And so we're going to talk here about different ways of trying to define this. So different ways people have thought about defining what it means to train or maybe even fine-tune a language model with privacy. So the setting we'll consider here is that there's a whole bunch of sources of data, of training data. These could be individual users of a system, like maybe the text messages of individual people. This could also just be different sources of text, say from the web, and we'll aim to provide some privacy for these users. And the way that we'll think of training a model here is typically that there's going to be some party that trains the model that first just collects all of this data, sticks it all in a big database, and then trains the model. And so one of the first ways we could think about privacy in this context, which is kind of inspired by the way we think about privacy in many other contexts in computer science and cryptography, is essentially as a notion of data secrecy, that there's this party here in the middle, this sort of central entity that collects all data, that essentially has to be trusted, right? So when someone trains a machine learning model, first they have to collect all the training data in order to train the model. And so, for example, if when Google trains their Gboard prediction models, they somehow presumably have to collect all the training data from all their users, from all the text messages that their users have written. And so we might consider that we do not trust this entity, this central entity, to see everyone's data. And so we want some notion of data secrecy. So how could we achieve this? So this is one notion of data privacy we might want, some way of essentially training a machine learning model without having to trust one party to collect everyone's data in the clear. And this is sort of a standard secure computation problem that people in cryptography have studied for decades, where in principle this is something that can be done, where you could have every data provider, every user encrypt their data, share the encrypted data with some central entity that at this point does no longer have to be trusted with the privacy of the data because it's encrypted, but this kind of orchestrates the whole computation to then in the end produce a model, an encrypted model that can then also be decrypted and used by everyone. And here there are techniques for doing this from the cryptography literature, so things like secure multi-party computation, homomorphic encryption, that in principle can be applied to any function we want to compute. So in particular, they can be applied to the function that trains a machine learning model on a whole bunch of data. But this is extremely impractical. It's sort of very, very slow and very, very expensive to do. And so this is not something that we can currently do in practice. So what could we do instead? So one more pragmatic way of trying to achieve this sort of desiderata here of training models on encrypted data is to, instead of using purely cryptographic solutions, to essentially try to leverage hardware solutions. So to have a piece of hardware that can process encrypted data without leaking this data outside of the hardware. And this is something that also there's been a lot of work on in the past decade or so. There's actually some of the newer GPUs that NVIDIA produces have such a confidential computing capability where essentially the memory on which the GPU operates can be encrypted and should in principle not be observable by the owner of this GPU. And so this means that in principle we could have a situation where again all the data is encrypted and collected by a untrusted entity that possesses one of these secure hardware modules, and then the data only gets decrypted within this hardware and processed there, and this should give you essentially similar privacy guarantees as with some of these cryptographic solutions we just talked about. This is a much more pragmatic solution. Here you can do this without much of a performance hit, but the security guarantees you get are a bit less clear in that they really depend on our ability in some sense to build hardware that doesn't somehow leak the data that it processes. And this is very much also an electrical engineering problem in some sense, and a lot of attempts over the past few years of building such forms of hardware have somewhat failed, and there's been lots of attacks on such systems. But these things are also getting better, and because it is really the pragmatic solution to this problem of sort of training on encrypted data, I think that this is the type of solution that industry will adopt in situations where you want to keep the data sort of private from the central authority that trains the model. Okay, so this is something you could do, but there's also other more heuristic approaches that people have considered over the years to try and efficiently enable sort of training on encrypted data. And one idea here that's been quite prominent that we'll talk about a bit in a bit more detail, it's a very sort of natural idea, is to somehow aim to train machine learning models on data that's somehow been encoded or scrambled. And so the idea here would be some form of weakening of encryption, where you don't encrypt the data that you send to a server, because that would essentially not allow the server to do anything with the data, but you somehow encode or scramble the data in a way that still makes it very, very hard to recover the data. So you still get a form of privacy, but that still lets you learn in a way. And it turns out that these two desiderata, essentially, to be able to preserve privacy on the one hand and to enable learning on the other hand, they're a bit in tension with each other. And we wrote a paper a couple of years ago that formalizes this idea, that essentially shows that if an encoding of data actually lets you learn, then it cannot really be private in a strong sense. And the idea behind this is actually quite simple. It's essentially, since you can train a model on this data, essentially, if the model is going to be useful, then the model must be somehow extracting information from these encodings. And so we can use the model itself to sort of learn new things about this encoded data. So here's just one example. Say you have a bunch of data that you want to train on that's been encoded, shuffled in some way that you think is going to preserve privacy, that you cannot recover anything from this data. And given such encoded data, it is possible to train, say, an accurate model for sentiment analysis. So a model that you can give a piece of data and it tells you whether the text that's as input has sort of a positive or negative sentiment. But then what we can do is we can just take any of the encoded pieces of data and just feed them into the model. And then, because the model is accurate, well, it presumably will tell us, this message is negative, this message is positive, and so on. And so in any case, the sort of the task that we're training on must somehow leak from the data. Like we will be able to label the data that we use as training data. But because of the way neural networks work, we typically can leak a lot more data here. Yeah, let me get to your question in a second. So let's so one thing that neural networks typically let you do is that their internal representations have some meaning, and in particular they let you do things like similarity search, or sort of compare instances and check whether they're similar to each other, or do transfer learning to other tasks. And so all of these things will also be possible on the encoded data if you are able to train if you are able to train an accurate model on this encoded data. So far I haven't really defined what it means to encode the data. So here, this is actually something we'll get to now, is sort of different ways in which people have thought about encoding data. There isn't really I would say, a formal definition of what such an encoding is. You can just think of this as some transformation that you apply to the training data that still lets you do learning. So it has to somehow be a transformation that keeps enough information about the data that you can effectively learn, but that should somehow give you some heuristic notion of privacy. So let's maybe look at some examples of what such encodings could look like. Maybe the most popular, the most prominent one is federated learning. So here in federated learning, what you do is that instead of the different parties sending their data directly to a central entity, the central entity essentially sends the current machine learning model to all the parties, and then the parties train this model or update this model locally, and then they send gradient updates. So essentially, the deltas between the current model and their edits to this model back to the server, and the server is going to aggregate all these individual gradients and perform a step of gradient descent, and then they send sort of the new updated model back to the clients and continue. And so if you notice here on this picture, there's now no longer any data that's being any training data that's explicitly being sent over. In some sense, the training data has been encoded in a different format, which is this gradient. And so this is one example of such a data encoding. Like we have data that's encoded, the gradients, that still allow us to learn, because they're essentially the entity, the data that we need for learning are these gradients. And the hope when federated learning sort of was first proposed, one of the benefits of this approach that people were claiming is that this also provides some form of privacy, because you are no longer sharing the data. You are now just sharing these gradients. And the problem is that this encoding actually doesn't really hide the data. And in the last few years, there's been many attacks that people have proposed that show that you can actually recover individual training examples from model gradients. If you have a batch size of 1 and you're essentially just computing the gradient of one example, then you're essentially leaking pretty much everything about this example, and that just instead of sending the data, you're sending some function of the data. And so as long as you can kind of roughly approximately invert this function, which is something we can actually do reasonably well for neural networks, you can just recover the data that gave you a specific gradient. And if you have larger batch sizes, this becomes a little bit harder, because you're essentially trying to recover now a mixture of many different training data points. But here also there's attacks that people have proposed that let you recover essentially all examples in a batch very effectively, even for batch sizes that are quite large. So in some sense, a gradient just doesn't really, even though it seems like it's a kind of an encoded version of a training data point, it doesn't really hide the data very effectively. And so this is an example of an encoding of data that is useful in the sense that it does allow you to train models very effectively, but it's not particularly private. To make things worse, here these attacks, these gradient inversion attacks, they're essentially they work for a completely passive central server. So here the server is not sort of even actively trying to break the privacy of the protocol. All they really have to do is just collect the gradients and then try to recover the data. And it turns out that a central server that's actively malicious can do even better. So there's some very, very cool attacks that have been proposed on federated learning. I call these weight trap attacks. So here the idea is essentially that the central server, right? They can send any model they want to the clients. That's kind of what they're trusted to do. And so instead of sending the real machine learning model, they could send a modified machine learning model where the parameters of the model are set in such a way, and this is actually something that's not particularly hard to do, so that when you compute the gradient of this model, of this sort of malicious model, you actually directly get the data back somewhere in the gradient. And so in some sense here, you're modifying the model so that the encoding sort of maximally leaks training data. And then the client is going to compute their gradients and send these back to the malicious server and sort of inadvertently completely leak their data by doing this. And here you get sort of essentially perfect reconstruction of some training data, even for very, very large batches. So if you look at the example here at the top for an image model, here even with an extremely large batch size of 16,000, this specific image was just completely leaked because it was directly encoded in the model's gradient. And you can do this for text models as well. There you get into there's some difficulties, some challenges that arise with doing this for text models because of the way transformers work. But essentially, it's the same principle, and you end up with a gradient that essentially encodes the input text of a small number of users. And so this really, this idea in some sense of federated learning, it's very nice from an efficiency perspective. In a way, it lets you kind of distribute training over many clients without having to aggregate all the data centrally and do all the training centrally. But it doesn't really provide by itself any meaningful notion of privacy. And so federated learning should really be understood as a way to distribute training, as a way of sort of improving the complexity, say, of training with millions of users or billions of users, but it's really not a way of directly improving the privacy of a distributed training algorithm. So people have then tried other approaches, and one that's also been quite popular for a while, where there's many examples of this paradigm, is to essentially try to build a sort of a weak form of encryption that happens to be machine learning friendly. I'm going to give it a specific example here. This is from a work called InstaHide that sort of tried to do something like this. As a neat idea that sort of on paper seemed to be doing something interesting, and then it turned out that it's actually also very much insecure. So the idea of insta-hide, I'm going to show it here first for images because it's a bit easier to illustrate, was to have some private data and also some small amount of public data that we don't care about the privacy of this public data. And this is usually something you can find quite easily. And insta-hide then does two operations with this data. First, it applies essentially a mix-up operation where you take all the data and you kind of just mix the data together. This already gets you something that seemingly hides a little bit, sort of some details about the data, but not all too much, right? You can still sort of recognize properties of the individual images. And then as a second transformation, essentially insta-hide looks at every pixel of the image, viewed here as a signed integer, say between -1 and 1, and then it just randomly flips the sign, and so all the pixels get sort of randomly flipped to a different value. And this now gives you these very grainy, very these images that seem to contain no more clearly visible information. So this seems to be maybe a pretty good encoding of data that's quite private. And what the authors of this method found out, which was quite intriguing, is that actually training on these completely grainy and noisy images still actually gives you an interesting, a good machine learning model. So somehow this encoding in some way is actually still contains some information about the training data that's useful, even though it seems like it really hides the input data. And you can do similar things for LLMs. So the same authors had a version of this called text hide that essentially applies a similar idea as insta-hide, but to the internal representations of a transformer. So this is a more general way of using this idea of essentially taking the inner representations and also applying this linear mix of different representations and then these random bit flips. And so this, and on the surface, this seems pretty private, but it turns out it really isn't. And a couple of years ago, we essentially took a closer look at this method and showed that it's essentially broken. And there's essentially two reasons why this is broken. The first of these is that this random bit flipping actually doesn't really do anything, in that you can just take an absolute value of all the pixels in the image at the end, and you will still get back something that looks a bit like the linear mix you started with, just with the colors kind of are a bit messed up. But for images, it's very easy to see here that you're now very much leaking information again about the private input. Like here, we can actually discern the head of the pig. We can see the strawberry, and so there's definitely data that's being leaked here, even if we have just applied some very, very simple operation like a pixel-wise absolute value. Really, what this also goes to show is that you should never rely on kind of visual signals to decide whether something is privacy preserving or not, because it's very, very easy to convince yourself that some data looks scrambled when in fact it really isn't. But so this is just one way of convincing ourselves that this method is really not all that private, and you can do the same thing with text, with encoded text as well. We then actually went a bit further and even did a full reconstruction attack. So the way the way this works is that during the process of training with InstaHide, you're going to encode the same private data. So in this case, this image of a pig with a strawberry, you're going to encode this multiple times. And every time the data is used, you kind of use a fresh encoding. And so this means that you're gonna mix your private data with different public data, and you're gonna redo the bit flips and so on. And the reason is just that this actually helps the model learn and generalize, that you kind of don't use the same encodings in every epoch. But now, because we actually know that we end up with a useful model, this model will have internal representations that allow us to do things like similarity search. So once we have a good model, we can very easily just take the encodings and sort of cluster them by similarity. And this is actually going to make encodings of the same private data look very close to each other. And so this is what our attack then actually does. It just takes it finds multiple encodings of the same images, of the same image. And then it turns out that if you just average these encodings in a smart way, mathematically, you're essentially kind of guaranteed to recover the original data. And the rest essentially acts like random noise. And so if you have enough encodings of the same image, you just get the image back plus a little bit of noise. So we actually ran this in practice. Like, we took the data released by the authors of InstaHide. So they actually had essentially a list of encoded images that they released, and had a challenge that asked the people to try and recover information about the private data. And so we applied this attack. We clustered the images by similarity, and then we recovered the original data, and we essentially managed to completely break this scheme and completely recover the encoded data. And so this again sort of just shows that this idea of training a model on encoded data just doesn't really work. If the data is encoded in a way that allows for learning a model, then it cannot really be private. And so really what we need, if we want this form of privacy from some kind of central data aggregator, we need a setting where we have cryptography or some form of trusted hardware. So where we can really encrypt the data using a strong cryptographic form of encryption, and then train a model on unencrypted data by first decrypting it, say in a hardware module, and then training a model. And this is, of course, either we do this with cryptography only, and then it's slow and expensive, or we do this with trusted hardware, in which case the security guarantees that we get are not completely clear at the moment. Okay, so this is kind of the setting of what we can do for when we sort of have a central entity that we want to trust for training a model. Here I'm going to also now talk just about a slightly different setting that we worked on recently, which connects a bit to these attacks we just saw on federated learning. So far we've considered a setting where we have multiple data owners that sort of want to train a model jointly. Now we're going to switch gears and look at a slightly different setting where we have a single data owner that's essentially just trying to fine-tune a model. So this is something very, very common today, right? Where you download some pre-trained model, say from Hugging Face, and you want to train to sort of fine-tune this model on your own data. Like maybe you have some very sensitive data, like some medical data, some financial data or something, and you want to download the model locally and fine-tune the model. And so in principle, this should be perfectly fine from a privacy perspective. What we show in a recent paper is that you actually have to be careful about what can happen if the model that you use for this, the sort of foundation model that you download and fine-tune, if this model is malicious, this could also have significant impact on the privacy of your training data. So the attack that we consider here, I'm going to talk about in a bit more detail now, is what we call a privacy backdoor. So the idea here is that some attacker is going to corrupt a model. They're going to put essentially a malicious model, say on Hugging Face. Then the victim, they download this model. And this is a model that's sort of been tampered with to help the attacker. And then they're going to fine-tune this model on their sensitive data, say on medical images. And what's going to happen is that because the model is malicious, it's somehow going to encode the training data inside of the model in a very, very specific way. And this is going to mean that after training, after this fine-tuning, if the adversary at any point in time gets access to the fine-tuned model, either directly to the weights of the model or even just API access to query the model, we show that the attacker can essentially extract some of the training data back. And so you can think of the attack here as what the attacker does is they embed some kind of trap within the weights of their foundation model that's essentially going to capture some of the fine-tuning data, and later on, by interacting with this model, the attacker can like recover the data. So this is sort of a new form of attack that we propose, which is very much inspired by these data traps that I talked about earlier in these attacks people had against federated learning. So this is actually the starting point of our attack. I'm going to describe here how this attack works in sort of a very simplified setting. So this weight trap attack, right? What it does is that this was in the context of federated learning, that the central server sends a malicious model to the client. The client computes one gradient on this malicious model and sends the gradient back to the central server in such a way that the gradient encodes some of the training data. And the way this works is by essentially just modifying the inputs, modifying the weights of the very first layer of your model. So we're going to assume here a pretty simple, just feed-forward architecture. You can generalize this to other models, and in our paper we actually do this. But for simplicity, we're just going to assume that the model takes as input a batch of inputs, and then it applies a linear layer followed by a ReLU activation, and then something else. We don't really care about what comes after. And the sort of insight here, this doesn't come from our work, this was from these previous works on attacking federated learning, is that if you compute the gradient here with respect to this weight of the very first layer, this is essentially a linear combination of all the inputs in the batch that happen to have a non-zero activation. So where this ReLU is going to be non-zero. And if you set, what you can do is you can set the weight, the parameters of this first linear layer, just so that very, very few inputs in expectation are gonna lead to an activation that fires. So if for pretty much all inputs, this this first layer is going to give you a value that's negative, and so the ReLU is just going to set everything to 0. And then for every once in a while, you get an input that gives you a positive value, and so the ReLU does fire. And then at that point, the gradient of the weights is exactly going to be the input. And so if you can observe the gradient, you essentially can observe the input that fired this ReLU. And so this is the principle behind these attacks. And this works sort of in a setting, right, where you immediately get to see the gradients that the victim computes. So this is in the context of federated learning, right? This is what the picture looks like. The adversary sends a malicious model to the victim computes one gradient. If in the batch there's an example that activates the ReLU, it gets captured within the gradient gets sent back to the attacker, and the attacker recovers the data. But remember that the setting that we're considering, which is this one, is where the victim is not just computing one gradient, they're computing an entire fine-tuning run. And only after this whole fine-tuning has completed with potentially many sort of hundreds or thousands of gradient steps, only then is the data, is the model accessible to the attacker. And so this is what makes the problem that we study a lot harder, is that we actually need data to be captured over many training runs. And if you just apply the same idea as before by having these data traps, the problem you're going to have is that your data trap is essentially going to be activated multiple times. And so maybe in one step you have one input that triggers your backdoor that activates your ReLU activation, and so you're going to get a gradient that encodes one piece of training data. Then in another step, maybe a different input is captured, and you get another gradient that encodes another piece of training data. And then over time, all of these gradients get added up to the weights. And so at the very end, if you look at the weight of the first layer of your model, what you're going to see is just a linear combination of all the inputs that got captured. And this is already interesting. Like if you captured very few examples, you're still going to get sort of a linear combination of just a few input samples. But what we would prefer is to have essentially a backdoor that captures kind of one input at some point during training, and that from there on is kind of no longer used. And this is what we show how to build. So essentially in our paper, we show how to build what we call a data latch, sort of inspired by the latches and sort of in digital circuits, which are essentially a one-time memory, right? A latch is essentially a digital circuit that lets you store one value, and then it sort of stops being used. And so the way we achieve this in the context of a ReLU network is we essentially just make sure that once an input is captured, once our backdoor fires and sort of our ReLU activation is positive, we are going to get a gradient update to the weights. And what we want to make sure is that after this first update, after the weights get updated once, from that point on, the activations are always going to be 0. And so the backdoor essentially can only be used once. And we can actually do this by essentially making sure that the SGD update to the weights kind of just reduces the value of all future values that will come out of this one unit. And so if you're interested in this construction, I invite you to look at the paper where we present this idea. So this is this paper here, privacy backdoors, stealing data with corrupted pre-trained models. We actually we take this idea and then show how to embed this into much more complex models. We do this in transformers as well. And essentially, we can build these one-time use backdoors that are going to fire just once at some point during training, like the first time that the activation is active and fires. We write the data essentially into the weights of the model, and then from that point on, those weights become useless, and sort of the activation never fires anymore, and so the weights never get updated anymore. And then at the end of training, by observing the model or by interacting with the model, the attacker can essentially read off these weights and recover the captured inputs. And yeah, as I mentioned, we do show that you can also make this work with transformers. This is a lot more complicated because of you need a whole bunch of sort of heuristic tricks to account for the fact that transformers don't use ReLU activations, that you have residual connections, that you have layer normalizations, that you have attention between different inputs and so on. And so it's a lot cleaner to do this with simple feed-forward networks, but the idea is kind of general enough that that you can do this for much more complex architectures like transformers as well. So this concludes the first part of this lecture on data privacy, where we essentially talked about data secrecy in machine learning. So the idea that we could try to train a model while keeping the data secret from a malicious party. And we essentially showed that this is, or we argued that this is an incredibly challenging problem, because there's many entities that you kind of need to trust for data secrecy. In that whenever someone aggregates data for you, be it the data directly or the gradients in something like federated learning, you kind of have to trust these entities with your private data. To make matters worse, when you download a model from some pre-trained model, say from Hugging Face, you actually also have to trust the developers of this model that they haven't tampered with it and added some backdoors in there, if you want to make sure that your data is going to remain secret. And the alternative is essentially that we need to use cryptographic techniques to really encrypt data before training on it, either by using sort of formal cryptography, secure multi-party computation techniques, or by relying on some hardware trust assumptions. And so this is still, I would say, pretty much an open problem at the time to be able to train models with while preserving the secrecy of the data during the training phase. And this is a form of model privacy, of data privacy, that we currently do not achieve, and that would be very nice to see some improvements, some progress on this problem. Yeah. Okay. Let me stop here for a short break, and then in say 5 minutes we can continue. And this now we're going to switch gears and talk about data memorization and differential privacy. Okay, so welcome back. And now in this second part, we're going to be talking about memorization and differential privacy for large language models. as a quick recap, what we talked about before here was that data secrecy is hard. That kind of, if you want to protect your data from some central aggregator, you need to essentially encrypt this data in a strong manner. One question from the chat is how we should view this in the context of differential privacy, if we couldn't view this also as a type of instance encoded data. We are going to talk about differential privacy in a bit, but yes, you can view differential privacy, in particular local differential privacy, as a form of instance encoding. This doesn't quite fit into our impossibility result because essentially the type of privacy that local differential privacy will give you is much weaker than what you get with say cryptographic encryption. So local differential privacy will by definition leak something about your data, but essentially in a controlled, in a bounded manner. And so this is in some sense the one way that you can hope to get an encoding that's sort of somewhat private and also somewhat useful, is by going through local differential privacy, but which in practice is just infeasible because the amount of noise you would have to add is way too big. But we'll talk about differentially private training a bit more in this lecture. What we're going to talk about now is essentially that's okay. We spent quite a bit of time on data secrecy and arguing that this is hard, that techniques are kind of slow and expensive. But to make matters worse, it turns out that this notion of data secrecy is kind of not enough. And the reason is that data that you train on can and often will be essentially memorized by the model. And so even if you do all your training of your model kind of in a private manner where the data aggregator never sees the training data, the final model itself might inadvertently leak some of the training data. So we actually saw an example of this with these privacy backdoors, right, just before the break, that this is a kind of a worst case example where a model is kind of engineered so that even though the attacker cannot see any of the data used during the training, in this case, the fine-tuning, the model itself at the end of training leaks the data. And so we, in some sense, need here a stronger notion of privacy that also accounts for the fact that the model itself might just memorize and leak data. So what we're going to talk about here are first, we're going to talk about this issue of data memorization and data extraction from trained models. Then we're going to talk about differential privacy as a potential defense. And we'll conclude by sort of some thoughts on what this means in the age of web scale pre-training and whether we actually still need these techniques or whether we can now sort of get privacy for free. So the issue we're going to be concerned about here is the fact that models memorize their training data. And this is something that has been known for a little while. So we first demonstrated this for language models in a paper on GPT-2, so one of the early precursors to ChatGPT. This was back in 2021, where we found that we could take GPT-2 and which is just a very simple, very bad by today's standards language model. We could feed this model from time to time. You could feed it completely random inputs. So this text here that says like East, Strasbourg, and continues with a bunch of other random words. And what comes out of the model is something very much not random, but something that the model has memorized from its training data. In this case, this was actually something reasonably sensitive. It was the full contact information of some person with their phone, email, fax, work address, and so on. And so this is data that exists on the internet. Like this model GPT-2 was trained on data from the public internet. But some of this data, the model just sort of fully memorized and sometimes spits out when prompted. So how do you extract this memorized text? Like how would you sort of quantify how much memorization is within a model? It's relatively, when we did this for GPT-2, it was a relatively simple pipeline. We essentially just first generated large amounts of text. And so for this, what's kind of nice is that even black box access to the model is perfectly fine. You just need to be able to generate lots of text. And then you just have a bit of a needle in a haystack type problem where you need to figure out among all of this text that the model has generated, what part of it is actually memorized. When we did this with GPT-2, we essentially did what we call a membership inference attack. So we tried to find data where the model was abnormally confident, where the model had sort of abnormally low loss. And then we just went and checked whether we could find this data somewhere on the public internet. So to visualize this is what this might look like. We might, sort of just get out a huge amount of just text from the model by prompting it with completely random inputs. And then by applying this membership inference attack, we actually find like a whole bunch of things in there that are verbatim, sort of word for word memorized from some websites on the web. And we found a lot of things in there, even though GPT-2 is a model that's trained on a relatively small amount of data by modern standards. You can find a lot of memorized news snippets and pieces of code and passages of books and people's some addresses, some phone numbers, some social media handles, and so on and so forth. So when we did this with GPT-2, it was mainly just a bit of a feasibility study. So we weren't really interested in extracting as much training data as possible, or even quantifying how much training data the model has memorized. But so now in more recent work, this is exactly what we did, because now the models are essentially trained on so much data on something that's essentially all of the internet, that if we want to test if some piece of data is memorized, we can essentially just check whether it exists on the internet. And so this is what we do now when we try to just quantify how much data a model has memorized. We essentially just take a model, feed it a whole bunch of random prompts, look at all the generated text, and then just check in an efficient manner whether this generated text kind of overlaps with part of the public internet. Here we set a relatively arbitrary but conservative threshold that we say that some piece of text is memorized if it exists word for word on the internet and it's at least 50 tokens long. So that's maybe something like 2-3 sentences of English, which is kind of long enough that it pretty much guarantees that this data wasn't just produced by the model by chance. So of course, for very small snippets, it's very much possible that a model would just generate some text that someone else has written before, but without having actually memorized it. Like there's only so many ways we can say certain things. But 50 tokens is kind of beyond this limit. It's like pretty much impossible to just come up with a 50 token sequence that exactly matches something on the internet, unless you're really copying it. And so then with this setup, we can take different language models and essentially ask the question, like, how much data do they memorize? Like, how often do they spit out training data when just randomly prompted? And here the picture looks roughly like this. So here we took just a few public open source language models, and as you can see, when we prompt these models and then just look how often they spit out something we can find on the internet, it's some small but noticeable fraction of the time that this happens, maybe up to 1% of the time the model generates something that exists on the public internet. And what's maybe even more worrisome here is that this trend kind of increases as the models get larger. So these are models here with 1.5, 7, or 65 billion parameters. And so as the models get larger, they also memorize a lot more training data. So these are these models here. These are what I would call sort of base language models. So a bit like GPT-2. These are just models that have been trained on data from the internet to just reproduce data from the internet. And so in some sense, it's not too surprising that these models might memorize and reproduce data from the internet, because this is exactly what they've been trained to do. But models like ChatGPT, or sort of most language models people use today, they then undergo other phases of training where the models are sort of aligned to respond kind of to user instructions, to act like chatbots. And so we were wondering if the same type, if we would still see data memorization and regurgitation in such models. And here for models like ChatGPT, you have to be a bit more careful with how you do this evaluation, in that if you just prompt ChatGPT with just some random string, usually the model is just going to tell you something like, oh, I don't understand what you're asking me, please ask me something else. Or even if you explicitly tell the model, like, here's a piece of text, please continue from this. Often the model can also just not do this. And so if we do the same evaluation as before, we essentially find that there's no memorization at all with ChatGPT. If we just prompt ChatGPT with random strings, the probability that it outputs something that we can find on the internet is essentially zero. And so at the surface, this would seem to indicate that ChatGPT has memorized a lot less training data than these other models, which it turns out is actually absolutely not true. It's the opposite. It just so happens that you need to prompt ChatGPT in a very, very different way in order to get it to spit out memorized data. And so this is what we described in one of our papers, essentially a different form of attack that makes ChatGPT spit out training data. I'm going to show the attack now. It's a very, very strange attack, and one that I must say we still don't fully understand why it works or how it works. So what we had found is that we could get, if you ask ChatGPT to just repeat a word forever, you get some strange behavior. So this is what's happening here. We asked ChatGPT to repeat one word, the word poem, forever, and the model does this for a while, and then suddenly it completely loses the plot and essentially starts acting a bit like a base language model again. Here it's just sort of generating something that looks like a news article about sports. It includes a YouTube video link. This essentially looks very much like the behavior we had come to expect from models like GPT-2, where it just generates text that sort of looks like some internet article. And it turns out that if you then look through this text, you find something that's copied word for word from the internet in something like 3% of cases. And so not only do we get memorized data out of the model through this very strange attack, but we get it at a rate that's much, much larger than with the other models we looked at here, which suggests that ChatGPT either is a model that's just much, much larger than these other models, but this we believe is not the case because it would be too expensive otherwise. And what's probably more likely is that OpenAI just kind of overtrained ChatGPT for many, many epochs, and so it memorized a lot more data than other open source models. So we have this attack that just asks the model to repeat the word forever. As I said, we don't actually really know what's going on with this attack, why it works. Our intuition or is essentially that, our hypothesis is that after saying a word too many times, the model at some point just kind of resets and acts a bit like it's at the beginning of a document, of a web document, and then just starts generating something random. This also doesn't work with all models. It worked at the time with ChatGPT 3.5. It didn't work with ChatGPT 4. It didn't work with some other models that we tried it on. So this is kind of a weird bug that we discovered here, but that somehow just illustrates that these models can actually and do memorize much more information than is apparent, and that sort of getting this information out sometimes requires very strange tricks. So to study memorization in models like ChatGPT in a more principled manner, what we then did is we looked at a stronger attack, which is essentially fine-tuning the model. So OpenAI lets you fine-tune their models, which means you can give some extra training data to kind of edit models like ChatGPT with. And so what we did here is we took some data from the internet, just some random Wikipedia articles, and we just took pieces of text and split them into a prefix and a suffix, and we just gave the model as training data the problem of essentially given a prefix, reconstructing the suffix. So we kind of explicitly trained the model to act like a sort of base language model again. That's like your new task is no longer to be a chatbot, but it's really to essentially autocomplete web text. And then we tested the model again on just kind of random prompts from other websites. So we didn't try to extract the data that we fine-tuned on. We tried to extract just any kind of data that the model would have originally memorized. And here we found that this attack was super effective, and we could actually get ChatGPT, both 3.5 and 4.0, to spit out training data in over 15%, was about 17% of prompts that we fed to the model. So these models have actually memorized. The base models here, our guess is that these have memorized a huge amount of training data. They've really been overtrained on web text, and that you can essentially recover this behavior through fine-tuning. We tested this with other models as well, with some of the newer OpenAI models, with some models from the Gemini family, from Anthropic, and we find memorization sort of in all cases, but different levels of it. And so this is a problem that tends to affect all models to some degree. This also doesn't affect just language models, or at least not just models trained for natural language. You can have the same problem with code, where models can sometimes regurgitate code that they memorize from the internet, and this has quite a few implications also for licensing and copyright. And it turns out that the same holds true for image generation models. So this is something we also looked at 2 years ago, was whether we could extract training data from text to image models, so like diffusion models. it turns out we can. So here on the right is an example of an image we extracted from Stable Diffusion, where on the left is the image that was actually in the model's training set. And on the right is the image that we managed to extract from Stable Diffusion, which is essentially just a noisy but pixel for pixel sort of accurate version of the training image. The way that we did this, that we extracted training images from Stable Diffusion, is essentially the same way we did for GPT-2 with text, is to essentially just generate lots of data and then filter the data that's likely to be memorized. Here we kind of cheated a bit because the data scale is so large, and we had an initial phase that essentially just tried to find good prompts, in that if you take a model like Stable Diffusion and you just give it some kind of random prompt as input, it's usually just not going to generate anything meaningful. And so you need to really be, you need to ask for the right thing. So what we did here is we looked through the actual training set of Stable Diffusion. So this was more this wasn't really an attack here. This was more a measurement study to sort of quantify how much memorization there is in a model like Stable Diffusion. So we went through the model's training set, Lion, and we just found examples of images that are highly duplicated. So here there's an example of a caption, I would say. We didn't actually look at the images, we just looked at the caption. This caption, Donna darts the goldfinch, scores blah blah blah. This appears many times in the training set, and so we hypothesized that these type of captions, these type of images that are highly duplicated in the training data, that these would be more likely to be memorized. So then what we did is we just prompted the model many times to generate images with this prompt. And you can already see here that there's evidence of memorization. But because we did this for thousands, millions of different prompts, we wanted a way to kind of automatically detect whether we found evidence of memorization or not. And so for this, we essentially just checked to see if there is some image that appears many times among the generations. And if sort of for the same prompt we generate the exact same image or very similar image many times, then we're quite sure that what we've generated is actually a memorized training image. And we can recover near exact copies of training data. So this is the original image from the Lion training set, and this is the one we extracted from Stable Diffusion. So it's really a pixel exact, just with lots of noise, copy of the original image. So you could ask here again, sort of, does this matter given that the whole data is public? So for example, this image I showed earlier of Anne Graham Lotz, who's an American evangelist. If you want to find this image, you can also just find it on Google. This is actually her Wikipedia profile picture. And so this isn't something particularly sensitive and something that's particularly hidden. So you might argue, well, who cares? Maybe, why should we care about the fact that we can extract these images from the model? And I would say there's two reasons we should care about this. One, which isn't really a privacy issue, but is more just a legal issue, is that this can matter for copyright. So here's another example. On the left, an image from the Getty Images database that was in the Lion training set. and on the right is what we generated with Stable Diffusion. And so this is an image that's actually licensed, that you're not allowed to just reproduce for free and without attribution. And so here there's already a bit more of a concern that you might just suddenly end up infringing copyright by just using the outputs of these models. And this is one of the reasons why many different institutions, different companies are actually suing model developers like Stability, who created Stable Diffusion, on copyright grounds. And the same is, of course, also happening with language models. OpenAI is being sued by the New York Times and by some others, also on the pretext that the models have memorized and can regurgitate training data. So this is sort of one reason people might care about a model memorizing training data, even if the data is public, is because the data cannot just be used by anyone for free. And then, of course, there's the issue of what would happen if we start training models on data that's not completely sort of benign, and where we train models on data that's actually a lot more sensitive. And one particularly concerning development here is this sort of trend towards training models on synthetic data. So the idea here being that if you have a generative model, so something like a diffusion model, and you have some very sensitive data, like maybe some medical data that you can't easily share publicly, what you could do instead is train a generative model, train a diffusion model on your very sensitive data, then generate a whole bunch of synthetic training data using your generative model, and then release that, or train models on your synthetic data. And there's a lot of companies, of startups out there that are sort of promising that this is kind of a way that you can get around privacy regulations, around GDPR and so on. And of course, here, if the generative model that you train on your sensitive data can and does memorize some of this sensitive data, then the synthetic data that you generate is not really synthetic, right? It might suddenly contain bits and pieces of the training data in there. And so if you then suddenly share this data, make it public, you're actually completely breaching the privacy of the data. So that's one reason why we might care about the fact that these models can memorize and regurgitate training data. So given this, we can now formulate another desiderata for what it might mean to train a language model with privacy, which is essentially, now we're not going to be concerned with the data aggregator. We just assume there's some process by which a model gets trained. But what we are concerned with is that an attacker who then interacts with the trained model might be able to leak information about the training data. And this is what we want to avoid. And this is what we'll call privacy, is essentially a model that does not leak training data after being trained. So how could we achieve this form of privacy? So here also there's a few heuristic approaches that can be considered that we'll talk about, and then we'll talk about a more formal way of achieving this through differential privacy. So one heuristic approach that you could try to prevent data extraction is essentially by just trying to filter out memorized data from the model outputs. And this is actually something that some companies do. So here's an example from GitHub's Copilot model, the code generation model. where if you give it a piece of code that's copied from the web, so this is an example of a function that comes from the Quake video game that you can find online in many different places, and that the model has very clearly memorized. At some point, instead of continuing generation, the model just stops and it will just refuse to generate more text. And the reason is because there's essentially a filter on top of the model outputs that just checks whether the current generation is part of the training data. This is something you could check quite efficiently using something like a Bloom filter or other data structures. But essentially here, every time the model generates text, you just check, is this something that exists in my training data? And if so, you just block the generation. And this sort of by definition prevents the model from ever outputting something that's an exact copy of the training data. There's two issues with this approach, though. One is that it only really works for exact matches, and as soon as you do some small transformations of your input, you might still get extracted. You might still be able to extract data. So here's two examples where we showed that you could actually get GitHub Copilot to still spit out pretty much exactly this piece of code, this function, by asking the model to spit out the function commented out. So here, instead of prompting the model with just the signature of the function, we prompted it with the signature of the function with a Python comment, and then the model is sort of smart enough to spit out the memorized data, but with the transformation applied. And now this no longer matches anything that exists in the training data, and so the filter doesn't apply. The example on the right is a bit more general, where we replace the variable names, in this case by we just translate them from French to from English to French. And so here also we just prompt the model with the header of the function, but with the variable name in French, and then the model spits out essentially the entire function, but with the variable names renamed to French as well. And this again is not going to trigger the memorization filter, because this exact piece of code doesn't appear anywhere on the internet. So this is one problem with these memorization filters, is that they just they only really match exact copies. Then the second problem is the fact that they do actually match all exact copies is also a bit of an issue, in that it actually gives you what we call a side channel to essentially just check if your data was used to train the model. And so the way this works is that, say you ask a model some very simple task, like say, repeat the word ABC, and then if the machine learning system, if the language model fails to do this, there's kind of two reasons why this could fail. Either it's because the model is just not very good and it just fails to follow the instructions, or because the memorization filter kicked in. And to be able to distinguish between these two cases, what we can do is just ask the model a very simple task. So maybe we give it, a piece of text that we repeat many times, and then we just ask the model, repeat this one more time. Here, if the model fails to do this, like any language model should be able to do this. And so if this doesn't work, then we're essentially guaranteed that this is because the filter kicked in. And so in this way, we can check whether ABC is in the model's training data or not. And this could be actually quite useful for some lawsuits, for example, where you could just prove in some sense that the model was trained on your data. So this we actually did with GitHub Copilot. Like, we took some repository on GitHub just at random, and for each commit that was added to the model, we essentially took the text of the commit and we just asked GitHub Copilot, like, can you repeat this piece of code? And then we checked whether this works or not. And we get a graph that looks a bit like this, where essentially any piece of code that's been added to GitHub after the 1st of October 2021, this always works. And so the filter is never triggered. And anything from before then, sort of the filter sometimes gets triggered and sometimes not. We're not entirely sure how their filter works and why it's this fuzzy, but we see this very clear kind of separation where starting from October 2021, the filter never gets triggered. And this is not a coincidence. This is exactly the cutoff date for Copilot's training data. So essentially any data from commits from before October 2021, these are in the training data. And so when we ask the model to repeat this code, we trigger the filter. And anything that's from after 2021, the filter sort of never gets triggered. And so you can essentially do this as a way to test if you have some repository and you want to check if it was included in GitHub's training data, you can essentially just check, does it trigger Copilot's memorization filter or not? So this is one heuristic that some companies are applying to sort of have an explicit memorization filter. We have to be careful with this. On the one hand, it doesn't filter out everything that we might want, and on the second hand, it kind of acts as a very direct oracle that lets us test whether something was in the training set or not. So another heuristic defense that people have considered is to essentially deduplicate the data better. If you remember, when we looked at data extraction for stable diffusion, we saw that one of the reasons why we can extract some images is just because they're duplicated very, very often in the training data. And this makes sense, right? If a model sort of sees some piece of data many, many, many times, it's just much, much more likely that the model will memorize it and suddenly spit it out. So here's one example. If you ask ChatGPT to complete the passage, it was the best of time, it was the worst of times, which is the beginning of a novel by Charles Dickens. Well, it's pretty much capable of spitting out the entire book. But that's also because this passage is like 500,000. You can find it like 500,000 times on the internet. And so it's maybe not too surprising that the model would memorize it if this exact thing word for word exists on the internet. And it turns out that properly deduplicating your data can be an effective way of preventing memorization. So this is something we had studied a couple of years ago, where we looked at how often a model spits out memorized training data as a function of how frequently this data appears in the training set. And what we found is that strings that are very, very rare in the training data, so strings that are only repeated maybe a handful of times or maybe just once, they are sometimes still memorized, but it's much, much, much more rare. And so there's a very, very small fraction of these strings that we were able to extract. Another thing you can observe from this plot, actually, so this we did with Pythia models at the time, is that you again see this very clear trend of scale, where the larger the models get, the more they memorize training data at all scales of duplication. And these were still very small models, right? This was up to a 6 billion parameter models, which is much, much smaller than some of the largest models that people train and deploy today. And so data deduplication is certainly a good thing to do. There's also a bunch of work that suggests that it doesn't really harm performance of the model to sort of remove exact duplicates of your data. But it also it's not sort of a bulletproof strategy. There's still going to be some data that's memorized. So this leads us to differential privacy, which is essentially a way to design a principled defense. So could we find a way to train a machine learning model where we can guarantee, where we can prove that there is no way that an attacker is going to be able to extract or to learn information about the training data. So formalizing this notion takes a little bit of work, and this took a very long time for the data privacy community to come up with the right definition for this. And this essentially led to the invention of differential privacy. So one way you could try to define privacy in this setting is to essentially say that anything that essentially the adversary who interacts with a machine learning model just cannot learn anything about users' data that they couldn't also just have learned without access to any of the aggregate data at all. So essentially, if you provide your data, you're not leaking any information whatsoever about yourself. And this is essentially impossible. Like if we actually want to train a machine learning model that's useful, there is some information, some aggregate information that has to be released. And so this led to this this other notion of privacy, this weaker notion of privacy called differential privacy. So here the way we define the fact that there's sort of no leakage of data is to essentially say that whether you as an individual provide your data to an aggregate, say, training algorithm, or if someone else were to provide data instead, this should be indistinguishable to an adversary. So kind of if you take one person's data and flip it, switch it out to someone else's piece of data while keeping all the rest of the data the same, an adversary shouldn't be able to distinguish these two scenarios. And so in particular, they shouldn't be able to learn anything specific about your data. They can still learn things that are true about the data distribution as a whole, because that's kind of the point of doing machine learning, but they shouldn't be able to infer anything about any individual data point. And so the way we formalize this is with the definition of differential privacy. Essentially say that an algorithm is differentially private, which is modulated by some privacy budget, the parameter epsilon. We say that this algorithm is differentially private if we take any two databases that differ in a single element, so two databases that are exactly the same except that one element is different in them. Essentially, if we apply the algorithm to these two databases, we get similar distributions over outputs. So here the algorithm that we consider is a randomized algorithm, and so when we apply this algorithm to a database, we get a distribution over outputs, and this distribution should be somewhat smooth and shouldn't change too much when we switch out sort of one user in the database. So I'm going to give I'm going to go through some properties and some facts about differential privacy in general in the next few slides, and then we'll see how to apply this to the training of a machine learning model. So as a simple example of what we can do with differential privacy, this is kind of the simplest possible case. We're going to look at computing a sum of data points privately. So here we're going to take a very, very simple example where each user is just has one bit of information, say 0 or 1, and we just want to sum these up. So this could be, say, a survey of all of my students at ETH to figure out like how many of them use ChatGPT. So each each student contributes either a 0 or a 1, and I just want to know how many of them use ChatGPT. And by default, if we just compute this sum kind of in the clear, this is not private, in that like if say there's a subgroup of all the students that I did this survey on, where all of these people know that they answered yes, and then the final result comes out and the result is also 10, then you can immediately infer that none of the other students in the class have answered yes, because this would be impossible, because the result that you get is exact. And so what we'd want here to make this private is essentially to release a noisy version of the true count, which should essentially be able to hide what any individual student, in this case, responded to the survey. Or more generally, if we're just computing a sum of different elements, that we get a noisy sum out that hides the contribution of any individual term in this sum. Okay, so to do this, we're going to need a simple definition, which is that of the sensitivity of a function, which is essentially the maximum amount by which a function can change when we switch out one element of the input database. So if we take any two neighboring databases, D1 and D2, and we apply our function to D1 and D2, what's kind of the maximum that the output can change for these two databases? So if we take our example of our previous example of computing a sum of n elements, like if we switch out one of the elements of the sum, so either a 0 becomes a 1 or a 1 becomes a 0, the maximum by which the sum can change is 1. So the sensitivity of the sum here for n bits is exactly 1. And this leads us to a very, very simple algorithm that is differentially private, which is called the Laplace mechanism. So what this does is we compute the function exactly. So we compute the sum of bits exactly. And then we add a noise from the Laplace distribution, which is a distribution that looks a little bit like the Gaussian distribution, but is kind of a bit narrower, sort of more concentrated towards 0. And we scale the noise. So the noise is centered at 0, but we scale the variance of the noise by the sensitivity of the function and by the privacy parameter epsilon. So if the function has higher sensitivity, we need to add more noise. And if the epsilon, if our privacy leakage epsilon gets smaller and smaller, which means we get more and more private, we also need to add more noise. And this is actually a super simple, super nice differentially private algorithm. We just compute the value that we want, and then we add a little bit of noise that's kind of scaled and calibrated to the sensitivity of the function. It's relatively easy to prove that this algorithm is differentially private. This essentially follows just from properties of the Laplace distribution. So, right, what we want to show in order to show that the algorithm is differentially private is that the probability that we get any output from a mechanism with either D1 or D2, the ratio of these two probabilities should be at most e to the epsilon. And so this we can directly plug in the definition of the sort of the probability density function of the Laplace mechanism in both cases, and things sort of cancel out, and then here we get this big exponential where we can apply essentially the reverse triangle inequality to then get this quantity here at the top in the exponential, which is exactly the sensitivity, right? The difference between the function at D1 and D2. This is bounded by the sensitivity. And so this gives us e to the epsilon. And so this is a simple proof that this Laplace mechanism is differentially private. And so we have a mechanism to get differential privacy for one function. This by itself, I mean, is already very, very useful. But what makes differential privacy in particular a very, very nice privacy definition is some additional properties that it has, namely the fact that it's closed under pre-processing and that it composes. By post-processing, we mean that if we have a function that's differentially private, if we then apply any other function on top of our differentially private function, so some other function f that does not depend on the data, then we stay differentially private. And so in particular, this means that if you release some data, or say if you train a machine learning model with some differential privacy guarantee, anything that someone then does with this machine learning model cannot really break the differential privacy guarantee. You cannot sort of lose privacy after the fact, as long as you don't look at the training data. So that's post-processing. And composition essentially means that if you have two algorithms that are both individually differentially private, then essentially any composition of these two, any function that aggregates the results of these two mechanisms, is also going to be differentially private with kind of the privacy budgets adding up. And so as you sort of release more information about the database, as you apply more algorithms to a database, the privacy kind of degrades in a nice and controllable fashion. And these two properties together mean that we can actually analyze much more complicated algorithms like gradient descent that we're going to talk about in a minute, and essentially analyze the privacy leakage that we get from a more complicated algorithm by essentially decomposing it into smaller chunks and then applying these post-processing and composition properties of differential privacy. Okay, so given that we're at the hour, let me take another quick 5-minute break here, and then after this we're going to talk about how to train machine learning models with differential privacy, so to essentially apply these ideas to the training of machine learning models. So see you again in 5. Okay, so we presented this definition of differential privacy and sort of showed how we could get differential privacy for something very simple, like sort of summing up some bits. what we really want here, right, is to do this for machine learning models, for something like a large language model. So how would we do this? So here, essentially, what we want is that we want some training algorithm. It's the training algorithm that's going to be differentially private, that takes as input a bunch of data, and we would like that the probability that we get sort of any model as output from this randomized training algorithm should be roughly the same when we switch out one training instance. So we want a training algorithm that is somehow very stable, that even if we switch out one of the training data points, we get essentially the same model as output. And so in particular, this will imply that the model cannot really memorize and regurgitate any individual training data, because this would violate this differential privacy guarantee. So the way we can do this is actually by a relatively simple, at least on paper, modification to gradient descent. So usually when we train machine learning models, right, we use gradient descent. We have some loss function that we're optimizing, and we take individual gradient steps. And the way that we make this private is by essentially having each gradient step be slightly noisy. And so instead of moving into the real direction of the sort of true gradient, we move into a slightly noisier version of the gradient direction. And it turns out that we can prove that this gives us differential privacy. And it turns out that this also can train models that are useful. So in sort of simple learning settings, like for convex functions and so on, we can actually prove that this private gradient descent algorithm is like converges, that it is just as good as standard gradient descent. It's like less efficient. You might need more data, but you will learn a useful function. And for more complex like neural networks, large language models, and so on, we can sort of empirically we can show that this works and still trains reasonably good models. I'll talk about the performance in a second. But first, let's look at what this noisy gradient descent algorithm looks like. So this is standard gradient descent, right? You sample a batch of inputs, you compute the gradient over this batch, you sum up all the gradients, and you take a gradient step. And this is really just a private sum, right, in each step. We take these gradients, which they're not bits, they're vectors of numbers, but we're just sort of taking individual elements that depend on each training data point, so these gradients, and we're just summing them up. And so we can actually apply the idea, so something like the Laplace mechanism we just saw, to compute a differentially private sum. The small difference is that here we're not going to use Laplace noise, we're actually going to use Gaussian noise, because we're dealing here with high dimensional vectors. It turns out that Gaussian noise is actually better than Laplace noise for this. A slight technicality is that this means that we're not going to get exactly the definition of differential privacy that we just saw, but a relaxed notion where there's an additional failure probability delta. But this isn't too important here. Essentially, we're adding Gaussian noise to each gradient sum to make it private. There's one issue we need to take into account here, is that, remember before when we looked at the private sum of bits, well, each entry in the sum is bounded, right? It could be either a 0 or a 1, and so we could sort of compute the sensitivity of this function. Here, in principle, we don't really know what bound to set on a gradient, like how large individual gradients could be. We might have exploding gradients, and we might have vanishing gradients, and so it's hard a priori to say how large these vectors can be. And so this makes it hard to reason about the sensitivity of this sum. And so what we're going to do is we're just going to enforce that gradients are bounded by clipping them. So what we do is we compute the gradient for each individual example, but then we clip it to some maximum norm of C. So essentially we take the gradient, we compute its norm, its L2 norm, and if it's larger than some constant C, we just shrink the gradient so that all the gradients are at most of norm C. And this means we can now compute the sensitivity of this function, right? If we have a whole bunch of vectors that are each individually of norm at most C, then their sum can change at most by C when we flip out one element, by 2C actually, when we flip out one gradient for another. And so by clipping the gradients, we kind of enforce that each gradient has some maximal contribution that it can have towards the final sum. And so we can bound the sensitivity. And we then add noise that essentially we set the noise, the standard deviation of the Gaussian, so that we can show that each gradient is or that one individual gradient is differentially private with very high probability. Then we need to account for the fact that we're not just computing one gradient, but we're computing n gradients, right? The whole thing here is within a loop that is iterated n times because we take like maybe multiple epochs of training. And so here, by essentially, thanks to post-processing and composition, we can then say that the entire training run is also going to be differentially private, but we just kind of have to add up the privacy budgets of each step. And doing this naively, essentially saying that, you know, one step is epsilon differentially private, and then the n steps would be n times epsilon differentially private. This would be correct, but would just be very, very, very conservative, very pessimistic. We'd get a very, very loose privacy bound. And so there's a bunch of extra technical tricks that are used to get a tighter differential privacy bound. The first thing here that we can exploit is the fact that in each step, we're not actually computing gradients over all samples, but we're computing them over a random batch. And so the fact that we sample this batch at random in each step actually provides some privacy in itself, because most data points are not used in every step. And so this is something we can incorporate into the analysis to get a better bound. And then the second technical difference with the naive analysis is that we can actually get better composition theorems than the sort of simple one that we looked at here, that just says that if we have n algorithms that are epsilon differentially private, we get an algorithm that's n times epsilon differentially private. It turns out that with a lot more technical work, you can show that this composition is actually square root n times epsilon differentially private, and so you can get a much tighter analysis of the composition of a large number of differentially private gradient steps by using these more technical analysis tools. I'm not going to go into the details here, but it's essentially to say that what's kind of nice here, taking a step back, is we can take this very standard gradient descent algorithm, and with very few changes, essentially the only changes we have to make to this algorithm to make it differentially private are to clip the gradients to make sure that they don't get too large, and to add noise. And then there's a lot of work that goes into the analysis of this algorithm to sort of figure out exactly how much noise we have to add. But in principle, this is a very, very simple algorithm, just doing noisy gradient descent, and you'll get differential privacy. The issue in practice is that if we want to prove a reasonable differential privacy guarantee, like maybe we want our epsilon, to be like some small number, like maybe epsilon equal to 1 or 2 or 10 or something. The amount of noise we have to add is huge. So here's an example from one of my works from a couple of years ago, where we looked at sort of the state of the art in training differentially private models on CIFAR10, so on a very, very simple image benchmark where we can get like nearly 100% accuracy if we don't care about privacy. If we do care about privacy, like at the time for epsilon equals 3, so a moderately large privacy leakage that we can prove, the best we could achieve in terms of accuracy was something like about 70% test accuracy on CIFAR10, which is like pretty terrible on CIFAR10. That's about as good as we could do before deep learning. So we can go sort of, like a decade earlier in time, and this is kind of what we could do at the time without privacy. So we kind of lose a decade of progress in some sense. These numbers have improved a little bit since. I think at the moment, the state of the art would be maybe something like 75 or maybe 80% accuracy on CIFAR10, which is still kind of lagging kind of a decade behind what we can do without the privacy guarantees. And so we do know how to train machine learning models that are differentially private, but this comes at a huge, huge cost in utility. So this brings me to the last topic I wanted to discuss, which is essentially combining differentially private training with this large scale, this large web scale pre-training paradigm. And the idea here, and this is essentially something that's gotten quite popular, is to essentially cheat a little bit and to say, well, we have these models, that are being pre-trained on lots and lots of data from the internet, on data that is publicly available. So we have these very, very good models already trained on public data. Then if I have some data that's particularly sensitive, all I really have to do is fine-tune this model with differential privacy. I don't really need to train from scratch. And so here, the privacy guarantee that you get is something a bit in between, in that you do get privacy guarantees for the data that you fine-tune on, like that the model is not going to memorize the fine-tuning data. But you get no guarantees at all for the pre-training data. And you just sort of say, well, this data is publicly available, so I'm not going to care about it. And if you're okay with this trade-off of essentially just saying all data that's publicly available, I'm just going to not care about at all whether my model memorizes it or not. And I only really care about the privacy for my fine-tuning data. Then you might be able to get much better trade-offs between privacy and utility. So here a couple of years ago, we did a study on this with fine-tuning of GPT-2 style models, where we found that even with relatively small epsilon budgets, so even something as small as epsilon equals to 3 or 8, we could get accuracies that were still not quite as good as the state of the art, as the non-private, but kind of getting much higher than what we can do when training from scratch. So here are actually some numbers for a specific fine-tuning task. Here you see that if you actually try to get differential privacy while retraining from scratch, you only really get accuracies that are sort of in the let me see if I can show this here. You get sort of these, for epsilon equals to 3, you get something like 15% below score by applying differential privacy when retraining from scratch, whereas the state of the art without privacy would be something like 69. It turns out that if we do differentially private fine tuning, we don't quite get all the way up to 69, but we get somewhere in the 60s. So we lose very, very little. So this is kind of an effective approach. One question from the chat that I'll address now. In federated learning, noise is added to the gradients or to the model parameters on the client side. So does DPSGD still function in this case? So yes, you can combine federated learning with DPSGD. So essentially what you do there in federated learning, right, the clients, they do some local updates of their models, and then they send gradients back to the central server. You can essentially add noise then to the aggregation that the server does of all the gradients. You just have to also make sure to compute the sensitivity of this sum properly. So essentially, all the clients can compute their own individual gradients, clip them to the right bounds, and then send them all to a central server that sums them up and adds noise. And this is how, for example, what Google does with Gboard models is they train using federated learning and differential privacy that's being applied at the central server. So here you do have to trust in some sense that the central server is following the protocol correctly, that they are actually adding noise properly. But if you trust that the central server does that, then you essentially get some of the nice distributed training properties of federated learning, plus the nice privacy guarantees of differential privacy. So still, when you apply differential privacy, you still have to be somewhat careful in how you do this, in that especially with text, it's not always super evident what the right privacy granularity should be for differential privacy. So remember that in the definition of differential privacy, we consider these two neighboring data sets that differ in one element, and you get sort of privacy at the granularity of such one element. But then it's a question of what you consider to be one element of your training data. So for a text data set, you could say, well, each word, each token is one element of my data set, and I get privacy with respect to the addition or removal of one token. But that's not a particularly useful notion of privacy. You could instead have privacy at the level of individual sentences or individual documents. The gold standard in some sense that you should strive for when deploying differential privacy is to have privacy guarantees somehow at the notion of individual users, that you have users of your system that provide data, and to essentially make sure that the contribution of one user is kind of the unit for which you provide differential privacy. This is not always super well defined. Like, you might be training models in some kind of collaborative environment where different users sort of share data with each other, or maybe different users just have secrets that they share, right? Especially when we talk about text data, you might be training a model on, say, the text conversations of different users, like in the Gboard case. But text conversations are inherently a way for people to share secrets with each other. And so even if we do get privacy guarantees for even if I do get privacy guarantees for sort of my data, that kind of whether my data is used or not, an adversary cannot really infer. There might be many other pieces of data that have been collected, say the messages written by my family members, by my colleagues, by my friends, that also contain private information about me. And so when dealing with text and applying differential privacy, you have to be a little bit careful about what the semantics of the differential privacy definition actually mean. But so now, if we're in this paradigm where we're doing sort of where we're relying on pre-trained models, on models that are pre-trained on lots of public data from the internet, and we kind of decide that we're not going to care about the privacy of the pre-training data, and we only sort of care about the privacy of the fine-tuning data. You could sort of take this idea to its extreme and ask, well, do we even need differential privacy anymore at all, or could we just use the fact that language models are extremely good at zero-shot and few-shot learning, right? So what does that mean? That when you have a language model like say ChatGPT that's been trained on all kinds of data from the internet, these models can very easily be adapted to new tasks without any fine-tuning at all, just by providing them with a few examples. So if you want the model to perform some new task that you have in mind, you just give the model in the prompt, you give it a few examples of the task, and then you just tell the model, well, these are the examples, now apply these rules to some new data. So you're essentially doing in-context learning, sort of learning of a new task on the fly. And this actually just gives you perfect privacy, because there's no more training happening here at all. You can just take your pre-trained model, that's been pre-trained on public data, and just apply and just do in-context learning on your sensitive data, and this essentially just gives you differential privacy with epsilon equals 0, so like perfect differential privacy, because you're not even doing any learning anymore. The model isn't being changed at all. You're just giving a prompt to the model and getting outputs back. And so if we really take this idea to the extreme, that we can use publicly pre-trained models without having to care about the privacy of the pre-training data, then it's not even clear that we even need differentially private training anymore. This comes with two big caveats. One is that the model you now have is really, it only provides privacy with respect to the evaluation data. It doesn't provide any privacy with respect to the pre-training data. And so all the concerns about, say, copyright violation and sort of privacy in a broad sense still remain, that your model might just memorize pretty much all of the pre-training data. And on top of that, it's not completely clear how well this sort of few-shot learning paradigm is really going to work in highly sensitive scenarios. And the reason is that so far we have quite a bit of evidence that in-context learning works very well. But for the type of tasks that people have evaluated so far, which are usually tasks that are, or data that's not too different from the type of data that was in the pre-training set in the first place. So the type of things you might find, on the internet. The question is kind of, if you have a very sensitive task that you care about, like maybe you collected some text from medical dossiers or from some highly proprietary financial documents or something, this is not data that you expect to exist anywhere on the internet. And so it's not clear how good pre-trained models are actually going to be at processing this type of data from scratch without any fine-tuning or without any training. And so if we really want to leverage publicly pre-trained models for very, very sensitive tasks, we also need better evaluation benchmarks, essentially. And this is something that there's still quite a bit of open questions and work to be done here to really see how well this sort of pre-training plus fine-tuning, or pre-training plus in-context learning paradigm really works for tasks that are extremely sensitive. Yeah. The other question, or the other direction that would be very interesting to see more work on, is to essentially figure out how good of a pre-trained model, of a foundation model, one could create if one were to actually try to remove most of the sensitive data that exists on the internet. So if we essentially took the internet and just sort of curated the internet and removed data that we don't really want the model to memorize, so say any publicly identifiable information, and then retrained a model like this, would such a model still be as good and as useful as say ChatGPT? So as an example of this paradigm, there's a very nice work 2 years ago by some folks at Berkeley, where they essentially pre-trained a language model only on data that's from the public domain. So only data that is permissively licensed, where there's no copyright violations that would happen. And then they combined this with a test time data store by essentially having data that's fed into your model in context at test time, and this data can contain licensed or copyrighted information. And they showed that this sort of by splitting up the data in this way, you could still get very, very good performance. But now your original model, your pre-trained model, you have much better control about what the model memorizes. And then at test time, you can sort of decide what pieces of data to feed into your model in a sort of retrieval augmented generation type way. And so this is a very, very nice paradigm. It would also be nice to see how well this works at larger scales, because of course this was an academic work, and so they mainly did this with relatively small models. But generally, the question that these works aim to answer is really sort of how good can we do? How good would public pre-training be for sensitive data that's not well represented in the pre-training data? So for now, when we kind of pre-train on everything that we can find on the internet, we tend to get models that are just very good at most tasks we throw at them, because typically the tasks that we evaluate models on are also represented somewhere in this pre-training distribution. But this might not be the case for most of the sensitive tasks that we care about. So the takeaways from this are essentially from today's lecture as a whole, is that privacy in language models can mean very, very can mean very, very different things. We first talked about secrecy of training data, of how we might want to train language models or machine learning models more generally, where where we don't have to trust some kind of central data aggregator or central model trainer. And we saw that this is very, very hard to achieve, and at least with current technology. Then we moved to a different form of data privacy, where we essentially want the model itself to not leak training data, that we want to know like test time leaks of models. And that here we essentially, there are some heuristic ways of doing this, but that really what we might want is a more formal, provable notion of privacy, such as differential privacy, which provides a narrow but a very precise privacy guarantee against inference of training data. But that even that is sort of, it's not clear if that's really the end for the story, and that one, it's just at the moment hurts utility quite badly if we want strong provable privacy guarantees. This can be alleviated by essentially using a lot of public pre-training data, but then we sort of have to rethink what privacy guarantees and what utility guarantees are we really getting in this setting. Yeah, so let me stop here. I'm happy to take any additional questions people have. I'll actually start with one from the chat, which was asking about yeah, so the position paper we had at ICML, so this is the one I mentioned a few times here in the notes, where we do suggest, yeah, that we need better benchmarks to evaluate differentially private sort of fine-tuning or differentially private in-context learning. It's not clear to me exactly what these benchmarks would look like. I do think, yeah, that they would have to be benchmarks where we look at definitely where we look at sample level privacy. So where we look at the privacy of individual elements of individual users in the data, but where also the what would be nice is to have benchmarks that evaluate the performance of models on tasks where we really care about privacy, and that today a lot of the academic work on sort of differentially private learning essentially evaluates models on the same type of tasks that everyone evaluates on. So just different types of, reading comprehension or text summarization tasks or so on. But these are not tasks that are particularly sensitive. And the tasks that are really sensitive, so things like, like processing medical documents or financial documents or other types of legal documents, we just don't really have any good benchmarks for these things, because this would actually require really collecting sensitive data. And so this is for me, this is a big open question of how much we can really expect current language models to help in this context. So also a follow-up question about federated learning. So when you do DPSGD in federated learning, you can actually ask the clients themselves to add the noise, and having different clients even setting different levels of noise. There are some systems there are some algorithms that let you do this, to essentially have a kind of a personalized privacy. You have to be a little bit careful how you do this, in that even if essentially if the clients add the noise themselves, you still need to kind of trust the central server to do the aggregation properly. Otherwise, the amount of noise that each client has to add would be very, very large. But this is how some of these implementations of federated learning with differential privacy work, that essentially all the clients compute their gradients locally, and then the clients kind of jointly compute or sort of make sure that the noisy sum is kind of computed correctly. And to do this with personalized privacy budgets is a little bit more complicated. But you can do this by essentially adjusting for each batch, kind of adjusting the privacy parameters that you use. Yeah. Are there any other questions from the audience here? Yes. Public data pre-training significantly increases the model utility. What if you pre-train on different modalities? So here you mean if you have a model that's pre-trained on text and images and audio and so on. My guess is this can only help to sort of make the models more generally useful and sort of easier to adapt to different scenarios. This is also something we don't really have particularly good benchmarks for, to have sort of benchmarks of different modalities. But yeah, it's an interesting question. I don't really know the answer to. I would say generally differential privacy from multimodal data is something that hasn't really been explored much. And so there's definitely a lot of interesting open questions there of how to do this effectively. Like maybe if you need to share the privacy budget across different modalities, or if sort of one modality matters more for privacy than another. There's some interesting questions there. Any other questions from the audience? And if not, I think we finish a little early today. Sorry if I went maybe a little bit faster on some aspects than in previous lectures this time. But yeah, thanks a lot everyone for attending. And of course, if anyone has any questions on this on these topics or on these works, I'm very happy to answer them also on follow-up questions by email. I'll also share the slides from these presentations with the organizers so that they can make them available.
Okay, thank you. So I just wrap up this lecture series on the AI safety and the privacy. I just want to thanks to the Professor Florian Tramèr for sharing his insights, and he really helped us think about the challenge we are facing and how we can tackle them. And let's keep this idea in mind. And thanks again for the Professor Tramèr, and thank you all of you for being part of this. Okay, thank you.
Yeah, thanks.
Okay, see you.
See you. Bye.
Bye.